So we've now introduced the definition of query models for three different types of algorithms, right? Classical deterministic algorithms, classical randomized algorithms, and bounded error quantum algorithms. And a nice feature of quantum query complexity is that we can show rigorous separations between these different models. Okay, so we can see examples of problems, where one model is potentially much more efficient at solving that than another one. And in this segment, I'm going to summarize what we know about the relationships between these three different models. Okay, so a very important distinction when we talk about this is between what we call partial versus total functions. Okay, so let me explain that first. So when we're talking about Boolean functions, a total function is one whose domain is all of 0, 1 to the n, so the whole Boolean cube. Okay. On the other hand, a partial function is a function which is only defined for a strict subset of 0, 1 to the n. Okay, so these are also called promise problems, right? Because you're promised that the input will come from this set S. So far we've actually seen more examples of partial functions, right? So, for example, in the Deutsch-Jose problem, we have this promise that our input function is either constant or balanced, right? So the problem is not defined on, any possible input function. It's only defined on this subset of functions that are partial or balanced. Likewise, this Simon's problem, right? It's only defined on the input function, has to satisfy this promise of being periodic. Okay, so these are examples of partial functions. So Deutsch-Jose we saw, so its quantum query complexity is just 1. Randomized, it can be solved with constantly many queries, but deterministically it needs omega n many queries. Okay, so when the size of the input is n, you essentially have to query the entire input. Okay, so this is an optimal separation between deterministic and randomized, and deterministic and quantum query complexity. Simon's problem also separates quantum query complexity from randomized query complexity. Okay, so the quantum query complexity of Simon's problem was order log n, whereas the randomized complexity is theta of square root of n. Okay, and this separation here turns out to be nearly optimal. Okay, so we know something slightly better now. So the K-correlation problem, so I'm not going to define that right now, but that essentially gives optimal separations between quantum and randomized query complexity. Okay, so for any constant q, it gives an example of a function where the quantum query complexity is q, and the randomized complexity is at least n to the power 1 minus 1 divided by 2q. Okay. So showing this randomized lower bound is non-trivial, very non-trivial, and that's done in this paper here. And it's known that this separation is almost optimal. So basically, if a function has quantum query complexity q, then you can actually design a randomized algorithm whose complexity is order into the 1 minus 1 over 2q. Okay, so this separation is essentially optimal, up to certain log factors. So this simulation result, if the quantum query complexity is q, then the randomized complexity is order into the 1 minus 1 over 2q. So it was originally claimed in this paper by Aronson and Ambinus, but later it's found out that that paper had a mistake in that proof. But luckily, the same result, is shown in a different way in this paper here. Okay, so that result still holds. Okay, so when we look at total functions instead, so again, total functions are functions that are defined on the entire Boolean cube, the situation is very different. Okay, so in fact, quantum and deterministic created complexity are always polynomially related for total functions. So now we actually know that the deterministic created complexity of function f is always at most its quantum created complexity to the fourth power. Okay, so this is quite a remarkable result. And we also know that this bound is tight. So there is an example of a total function f whose deterministic created complexity uh, actually does require the fourth power of its quantum created complexity. Okay, so we actually understand the relationship between deterministic and quantum created complexity for total functions quite well now. In the randomized case, so the situation is similar, but we still have an open problem here. So for randomized, the randomized complexity of f, we again know the same bound. It's always at most the quantum created complexity to the fourth power. And here, we just know an example of a function whose randomized complexity requires almost the third power of its quantum created complexity. Okay, so here we still have this gap between the 4 and the 3, and the current thinking is that actually it's this upper bound which should be able to be improved, and that the right answer is the third power.